Welcome back, everyone. In this video, we are going to walk through collision theory. Your textbook calls this simple collision theory. So I don't know what complex collision theory is. I don't know that I've ever studied it, so I'm just going to call it collision theory. Okay, so in this, I'm not going to do the full derivation. You can find the full derivation in your textbook. But I am going to go over kind of the key assumptions that we use as we are going into that derivation, because these assumptions are going to apply once we finish. So we are going to assume that we are working with a bimolecular reaction. So this means that two reactants collide for the reaction to proceed. So in our case, we have A plus B goes to form some products, and that reaction has a rate constant K. In order for this reaction to occur, the reactants must be close enough for the intermolecular forces to be important. And so this means that A and B have to get close so they see each other. This is what we call the collision. We also assume that a single distribution function describes the probability of a reaction occurring for any such collision. This is really going back to that Boltzmann distribution. And so basically we can say that A and B both fit a Boltzmann distribution of speeds, and with those Boltzmann distributions of speeds, we can predict the likelihood of a collision occurring. Now, also, there will be some activation energy that needs to be overcome with this collision. So A and B have to collide with the proper amount of energy. So once we set up the Boltzmann distribution and we start thinking about how A and B, based upon their probabilities of speeds, what it looks like whenever they collide, we find that the rate, this is the rate constant, is equal to this complex term times this simple term. And the simple term is this e to the minus EA over RT. Okay? Now, when we think about this complex portion, we are working with where sigma AB, this is our collision cross-section. And so this is really talking about how big A and B are, so that they can be able to collide. Mu is what's known as the reduced mass, and it is given by this formula. It's basically a ratio of the masses involved. So this is really trying to go from the Boltzmann distribution, remember, had mass in it, but the Boltzmann distribution was only thinking about one component. This mu is working to find the mass of more than one component. In A is Avogadro's number. It is what is going to help us figure out how much stuff there is. P, this is the steric factor. So this is what we were talking about in the last video of what is the likelihood that A and B can collide together with the correct orientation and that there's nothing in the way. And then the last piece is EA. EA is the activation energy. So thinking about the energy needed to get over the barrier in order for the reaction to occur. Now, this collision theory all of this is our complex part. There's a lot going on in here. What we do is we like to use Arrhenius because what happens is that we take all of that and we combine it together and we call it A. And A is what is known as the pre-exponential factor. And so it is working to talk about the collision frequency, the steric factor, the mass, the concentration components, all of this in one compact, experimentally determined variable. So really, we've just combined variables together. And notice that this e to the minus ea over rt is the same in both of these. Now, this rate equation, this is the Arrhenius equation. And you have probably seen this before. We used this in Gen Chem when we talked about finding the activation energy. And now the next videos that we're going to talk about, we're going to start digging into what this activation energy is and how the rate factors into that, and how knowing the rate can help us figure out the activation energy.